Hi, I'm Sheban Chow from Department of Information Engineering, the Chinese University of Hong Kong. Our work to be presented is cross-domain access control encryption, which support arbitrary policy, constant size ciphertext, and being efficient. To recall our contribution in these 15 minutes, look at these adjectives start with A, C, and E. This is a joint work with Xiuhua Wen, my former PhD student who recently joined HUST in China as an associate professor. Let's consider the classic access control model that assigns role to every user in the system, such as public or top clearance. In this work, we use an identifier or ID to represent each role, and we use a matrix P for the access control policy. For example, user 1 here can only write to user 1, while user line here can write to all users. In general, such a matrix P can capture the access right between all user pairs, which is what we meant by arbitrary policy in this work. To enforce read access, we can use encryption. How about write access? A lateral flow is to use signature. For example, a user sending a message M needs to sign on M, and the receiver will drop any M if the signature is invalid. Does this approach work? To answer this question, we first need to recall why do we want to enforce access control over write access. An answer is we want to protect against malicious writer from writing or leaking information. So what is a malicious writer referring to? Consider a CEO who is not supposed to leak top-level secret to anyone, say an intern. Would the CEO intentionally leak the secret? Probably not. However, the program used by the CEO might be infected by virus. It will call a home server to report any gathered secret. Would this home server bother with a signature check? The answer is no. Indeed, a malicious writer can simply just broadcast the gathered secret information in key, or embed it in the randomness of a ciphertext, or by whatever single logarithm technique. So, to guarantee any meaningful security, we actually need a sanitizer, or traditionally, we need a trusted reference monitor. Access control is a fundamental keystone in security. Many data breaches can be avoided if we have secure access control enforced, no matter that is a cryptocurrency wallet, a smartphone app, a running process, or a cloud tenant. Access control encryption, or ACE, is a cryptographic solution for enforcing information flow. It is introduced by Guy et al. In TC 2016. Their work showed that cryptography can actually also help in enforcing write policies. The sanitizer they assume is honest but curious, which does not even need to load the message or the policy of each ciphertext, but it can still sanitize the communication traffic somehow according to the hidden policy in a blindfolded manner. Since this seminal work, there are two major follow-ups appeared in PKC 2017 and AsiaCrypt 2017. We will refer to the latter one slightly more frequently in the rest of the talk. ACE. In ACE, that is different from traditional public key encryption. One actually needs to be granted an encryption key to encrypt, and this ciphertext will be sent to a sanitizer. The sanitizer will apply sanitization process, and the resulting sanitized ciphertext will be sent to the receiver, who then decrypt the ciphertext. We looked at it is more desirable for the sanitization process to be keyless, since we do not want to store a secret sanitization key in a machine that is practically always online for sanitizing the outgoing traffic. So, who will generate the keys? In ACE, a single trusted authority will generate both the encryption key and the decryption key according to the security access control policy to different users. So there will be an encryption key and decryption key for Alice, and likewise there will be an encryption key and decryption key for Bob. The first contribution of this work is to propose a new notion lambda cross-domain ACE, where we separate the key generation authority into two, the sender authority and the receiver authority. One will only generate the encryption key, and another will only generate the decryption key. This better captures real-world application scenarios. Security of ACE ACE should ensure low-weight rule, such that any set of co-op senders cannot transfer any information to any set of co-op receiver when the communication is forbidden by the policy P. This is captured by the indistinguishability between sensitizing two kinds of ciphertext, one from the adversary and one freshly created. ACE should also ensure the low-read rule, namely, the payload should remain private, and no one should learn who the sender was. A weaker version of sender anonymity only considers such protection against long receiver. In a nutshell, ACE can enforce access control blindfolded, which is very powerful, but turns out existing constructions are also very heavyweight. Our result is ACE can be made practical. Let's see how ACE schemes were constructed. It can be roughly classified into two paradigms. The first one starts with constructing a simple but efficient ACE. In the seminal work, an ACE scheme for one user is first built by using algorithmic encryption. Its homomorphism helps to perform sanitization. But upgrading the one user scheme to support arbitrary policy requires exponentially many copies. We remark that one can also replicate a symmetric ACE to support range policy ACE. Another paradigm directly constructs ACE using functional encryption, or FE. Recall that in FE, a functional key of F can decrypt encryption of M into FM. Demgard et al. Proposed an ACE scheme using sensitizable FE, which is instantiated by indistinguishability of falsification, which is extremely heavyweight. Kim and Wu's construction use FE for randomized functionality. The function here first runs a signature verification algorithm. If the signature is valid, it will create a new ciphertext under a predicate encryption scheme. This construction is still inefficient, since FE for general circuit is still heavyweight. This work aims to solve the open problem left by the seminal work, which is to design sublinear ACE scheme with practical efficiency. Note that Kim and Wu's approach used a functional key as the sensitization key. They left as an open problem to construct an ACE scheme for general policy where the sensitization can be keyless. We solve both problems. Our solution is based on structure-preserving signature and identity-based broadcast encryption. You may wonder what this length means, or if you're a cryptographer, you may wonder if it is a simple construction or not. We would say it is a natural solution in hindsight. We observe that supporting arbitrary policy means encrypting to many recipients. It is then natural to use broadcast encryption, in which encrypting to n recipient only takes constant size ciphertext. As simple as it may seem, we still need to address several challenges or introduce new ideas in various stages of our design. To start with, let's quickly review Kim and Wu's ACE scheme and why it fails to support cross-domain feature. The encryption key is merely a signature on the sender ID. It means that the sender authority has no control who can decrypt. It is actually the receiver authority who runs the PE system can make the sole decision on who can decrypt. And by the way, for this construction of encryption key, it makes proving the correctness of encryption simple by using lizard proof. Now, let's consider how to prove the one-to-many permission to the sensitizer. Broadcast encryption ciphertext can be of constant size since they employ a compact encoding of all receiver identities. However, a complicated structure takes a complicated proof. The proof could be exponentially long since it's capturing the right permission to many recipients. Our approach is to extract the order 1 representation of the recipient set as a group element, and we call this concept an aggregator. In our construction, an encryption key is still a signature, but now it is silent on the receiver set. For this, we need to use structure-preserving signature since they can sign on a group element. This also makes the proof in the ciphertext constant size. The next question is, how do we sensitize without using any secret? Indeed, The seminal work already said that a simple approach which not use FE but use listed proof does not work. And the reason is that the sanitizer in this case needs to load the public key of the receiver for randomizing, which means to sanitize the ciphertext. And all the FE-based scheme circumvent this problem by using a secret functional key to create a sanitized ciphertext instead of literally do the sanitization over the original ciphertext. So, how can we solve the original problem in our design without using FE? That means we are facing with the following problem. How to enable the sanitizer to sanitize an order one size podcast encryption ciphertext without letting it load all the recipients. For here, we use a simple prepare ahead approach. Namely, the sender is required to prepare a sanitization ciphertext C' of message 1 and the payload ciphertext encrypting the actual payload. Both of these components can be proven to be well-formed in NICK proof. With that, keyless sanitization is easy, which is simply a homomorphic operation. Finally, for decryption, any recipient can decrypt by operating on the same order 1 structure in the ciphertext derived from the aggregator. Decryption does require loading all other recipients. In this way, the recipient can infer who the sender is. It means that, unfortunately, our scheme only achieves a weaker notion of sender anonymity. Nevertheless, it suffices for all the original application envisioned in the ACE literature. It also matches the anonymity level of existing ACE schemes, and technically, this appears to be an inherent trade-off between anonymity and the ciphertext size. So, we quickly highlight how do we do encryption and sanitization and decryption efficiently. So have we solved all the problems yet? It turns out that instantiating our design efficiently and securely is still not that easy. What we mean by security is adaptive security in the standard model. Our main scheme is selective secure, which matches the security level of Kuehnelt Wurtz construction. We look there for achieving adaptive security. We actually need to solve a new open problem. Nevertheless, using existing building block, we managed to propose an imperfect adaptive secure ACE, the detail of which can be found in the paper. Let's focus on our main instantiation. We use Sakai Furukawa IBB scheme, Abed et al.'s structure preserving signatures, and Fiat-Shamir heuristic for the proof. To demonstrate the efficiency of our instantiation, we use a somewhat old computer for performance testing. Our implementation used Java PBC library and 462-bit BN curve, and we didn't do any preprocessing in our prototype. To get a sense of how fast or how slow our platform is, here are some sample figures. For example, we do all the pairing operation without any special preprocessing, and each of them take around half a second. Here are the running time performance. Authority setup, encryption key generation, and a special helper function for decryption, they are all set size dependent, so we can see that the runtime increases linearly. All the other algorithms are set size independent. We can see that all algorithms run in the order of seconds, even for 1,000 of receivers. To conclude, access control is a fundamental keystone in security. ACE is a cryptographic solution enforcing information flow by assuming an honest but curious sanitizer. Non-ACE design use general-purpose cryptographic primitives, which are heavyweight. Our work made ACE more practical. We also consider ACE in a more elastic cross-domain setting. Finally, the seminal work also asks a second open problem, namely to construct ACE from noisy post-quantum assumptions such as learning with error. Our work to appear in ACNS this month proposed a lattice-based construction addressing this problem. We can be contacted at this email address, and now we are happy to take your question. Thank you.